Day 99 Notes, Advanced Algebra 2. Yesterday in our note session, we worked on the average rate of change, and we recognized that average rate of change is just a phrase that represents the word slope. The average rate of change between 2 points or between 2 points on a function is simply the slope between those 2 points. And so we looked at a lot of different examples there. We considered some real-world problems, and then we had a chance to practice some of those real-world problems from the assignment that was given to us for last night. Today we're looking at specific slopes and how they create relationships between lines, and in particular what we're focusing on are parallel and perpendicular lines, only with linear functions. So we're not going to deal with any functions that curve over time. We're only looking at straight line linear functions. So some of this is going to be familiar to you. I'm sure that you'll recognize some of the techniques that we have. I'll also be talking about some other techniques that you may not be so familiar with, but I encourage you to practice, pause, and replay this video if you encounter something that doesn't make sense the first time you see it. Now, the first thing that I want to remind you of is that our standard form, or the most common form of equation that we use to represent linear functions, is this: y equals mx plus b. This is what we call the slope-intercept form. Slope-intercept. Let's write it as one phrase here. The slope-intercept form of a function. And we recognize that this is the slope-intercept because the slope of the line is given to us here. It's the number written in front of the x, and the intercept is given to us here. And don't forget that this is a y-intercept, not an x-intercept, but a y-intercept is given to us here. So anytime that I encounter a function like this example down here, we can replace the letter y with f of x because that's function notation, but the pieces on the right should be familiar to you as well. 3x plus 5 means that this particular line has a slope of 3 and an intercept of 5, a y-intercept of 5. And so in this sample problem down here, if this is what we were given, let's try to find a line that's parallel to this with a y-intercept of 2. Now, we briefly talked about parallel lines at the end of last week, and we recognized that parallel lines are two lines that are drawn side by side. We know that they'll continue on forever in both directions, and they'll never cross one another. Well, if we put those two lines on a coordinate grid and we calculate their slope, if we determine their rise and run to repeat points on this line, the rise and run for each line would be exactly the same. So when we're talking about parallel lines, we're talking about two slopes that are equal to one another. And with that in mind, this first question should be relatively quick to answer. Let's identify an equation of a line parallel to f of x with a y-intercept of 2. Now, since our problem is giving us function notation, let's go ahead and respond with function notation. I'm not going to use f of x again because we already have a function called f of x, so let's call it g of x this time. G of x would have to have the same slope as our first function, so I know that the function has to start with 3x. The slopes are the same. And for a y-intercept of 2, well, the y-intercept is listed here as our b value in the mx plus b equation. This is our solution to the question. 3x plus 2 would be the equation of a line parallel to f of x with a y-intercept of 2. For this next question, I want you to think about it a little bit differently than you may have seen it in the past. Let's start with a quick sketch of what this graph might look like. I know that it has to have, I know this has to be a line parallel to f of x, so its slope is 3x, and it goes through the point 1, 4. So if I go over 1 and up 4 units, that would be a position on that line. Now from here, since the line has to be parallel to f of x, let's call this one h of x, since we use g of x as well. We're starting off with 3x, that represents the slope of the line, but what we need to do is find the intercept. We need to find the value in which the graph will cross the y-axis. Now, to do that, we again recognize that we have a point here at 1, 4, and we're trying to find the point where it would fall on the y-axis. What you can remember from here is that the slope indicates our behavior. We have a slope of 3, so that means that it rises 3 units. 1, 2, 3 units, and it runs 1 unit. And if we rise 3 and run 1, that should place another point on our function. And conversely, we can go in the opposite direction. We can go up 3, 1, 2, 3, and to the right 1, and that would represent another point on the line. I'm not so interested in this point up here, though, because this one is the value that gives me the y-intercept. And this graph will cross the line, cross the y-axis at a positive 1. So we'll use positive 1 in the equation here, and that represents the equation of this line. It has a slope of 3, which would be parallel to the original function, f of x, and it has an intercept of 1. With those two criteria met, we know that it's a line that will cross through 1, 4. Sometimes discovering or calculating the appropriate equation can be a little bit more difficult, and for that we use the point-slope formula, or the point-slope form, in order for us to identify the correct equation for an equation that we're trying to accomplish or trying to determine. In this case, we need an equation of a line that's parallel to f of x. So I'm going to call this one j of x. I don't like using I of x because that looks too much like the imaginary number I. So I'm skipping I and I'm going to j of x here. J of x has to start off as 3x because that's what would make this slope parallel to f of x. But the only other information we have is that it goes through the point -2, 1. Now, I could use the other technique, and I could plot the equation, or I'm sorry, plot the point -2, 1, and then rise 3 and run 1 each time until I reach the y-axis. But here's another technique if you're more inclined to use the algebra to solve that. We have what's called the point-slope formula, and that looks something like this. Y minus y1 equals m times x minus x1. The way we would use this form is we would replace this y subscript 1, we would replace x subscript 1, and the letter m with numbers from our given problem. Now, m clearly represents our slope, so we have that already. y1, that y1 represents the y variable of our given point, and x1 represents the the x variable of our given point. If I replace these three values with the numbers that I have given to me in this problem, I can then use some algebra to rewrite this equation from point-slope form into our slope-intercept form. And by the way, you'll notice that this equation, this type of form, gets its name from the two items that we were given. We were given a point and the slope of a line. When we have a point and a slope, we would use the point-slope form. Whereas if we were given a slope and an intercept, we would use the slope-intercept form. Let's take a look at what happens here. I'm replacing the letter y1 with the number 1. Notice that there's a subtraction sign here, so y minus 1 equals m, which we know is 3. That's the slope that we have to use here because it's parallel to the original, times the quantity of x minus x1. And x, in this case, x1 is a -2. With our values replaced, it's just a matter of algebra in order to solve this equation. Now, what I like to do is just simplify the left-hand side of the equation. If there was a negative sign in here, I would change this to y plus 1, but it's not a negative, it's just y minus 1. No changes there except for the loss of the parentheses. Then I'm going to simplify the inside of this set of parentheses. X minus -2 is the same as x plus 2. Next, I'm going to look to simplify the right-hand side of our equation further, and I'll distribute the 3 to both pieces on the inside of my parentheses. I have 3x plus 6 here now. Lastly, in order to get y by itself, which is traditional for our slope-intercept equation, I'll set y equal to 3x plus 7. And don't forget, I got this 7 by adding 1 to both sides. When I add 1, it cannot combine with the 3x, because this is a different value. But I can add 1 to this 6, which is a constant. 3 and 1 makes 7. So back over here, if I'm talking about my solution, my equation of a line parallel to f of x through the point -2, 1, then this has to be at the point, or I'm sorry, this has to be the equation 3x plus 7. So those are 3 examples of how we can work with parallel lines. Let's now take a look at perpendicular lines. Again, if at any point in this video some of the processes or procedures don't make sense, please pause the video and rewind and rewatch. That'll help you hopefully understand the techniques that we're showing you here today. Before we move forward with answering these questions here, let's remind ourselves of how we can change our slopes to create 2 lines that are perpendicular to one another. Perpendicular lines are those whose slopes are opposite reciprocals. They're opposite of one another and they are reciprocals. So opposite means that we change the sign from positive to negative. So we change the signs, positive to negative, and reciprocals mean that we flip the fraction. If there's a fraction that represents our slope, we need to flip that over, and that's what would make it a reciprocal. So if we know that a particular function g of x is equal to 2/3 x plus 2, then the line perpendicular to it, let's call this one f of x, the line perpendicular to it has to have a slope of -3/2. It's a negative sign because we originally started with a positive sign, so we're changing it. That makes it an opposite. And then a reciprocal means that we have to flip this fraction over. So we're now dealing with the fraction -3/2. If our y-intercept is supposed to be -5, whoops, can't move too far. We've got to put an x after that slope. If our intercept is -5, well, we just follow up with that. And now we have an equation in slope-intercept form. In this next example, we need to find the equation of a line perpendicular to the original, and this time it goes through the point 2, 0. I'm going to use the equation h of x, and I know that the slope has to be -3/2, again, because that's perpendicular to the original. So my slope is -3/2. What I don't know is what the intercept is just yet, so what I'm going to do is use the point slope formula again, because I know what the slope is, I know what a point on that line is going to be, so I can use this formula. Y minus y1 equals m times x minus x sub 1. Replacing values here, I have y minus 0 equals -3/2 times x minus 2. Y minus 0 equals -3/2 x minus 2. I can distribute and actually simplify on the left side right at the same time, because what is y minus 0? Well, that's simply y. On the right side, we can distribute this coefficient out front, and -3/2 times x is just -3/2 x, and -3/2 times -2 is simply +3. Now let me remind you how we got that. If I have 3/2, a -3/2 times a -2, that would have been the same as -3/2 times -2/1. When we multiply fractions, we can multiply straight across. And let's call this a -3 times a -2, that's 6. And then a +2 times a +1, that's 2. And 6/2 reduces to 3. That's how I got my solution over here. Now, wouldn't you know it, this solution is exactly what we were looking for, except we're not going to use y, we're going to use h of x. That's h of x equals negative 3 halves x plus 3. And we now have our solution. Now, in this problem, or any of these problems for that matter, you could imagine what the graph looks like, and you could move along the slope pattern to find the y-intercept. That technique is perfectly fine, but I do want to show you this point slope formula for these last two examples so that you can at least see that in action and decide if this is a method that you want to use as well. Now, we can use point slope form again here because we are given both a point and the slope of our line. The slope has to be negative 3 halves again because it's perpendicular to the original. So the slope of negative 3 halves multiplied by x, and now we need to find our intercept. So we'll go with y minus 8 equals negative 3 halves times x minus negative 2. Y minus 8 equals negative 3 halves x plus 2. And y minus 8 equals negative 3 halves x plus, I'm sorry, not plus. This one will become minus 3. Because again, if I'm multiplying negative 3 halves times a positive 2, that's positive 2 over 1, that equals negative 6 over 2, and that reduces to negative 3. Now we didn't luck out this time. We're not quite finished because I haven't solved for y yet. So I do need to add 8 to both sides, and we have negative 3 halves x plus 5 as our end result. And so again, final solution, j of x is equal to negative 3 halves x plus 5. The slope was the easy part. The intercept was a little bit more difficult since we had to go through the point slope form in order to achieve that final result. Before you get started on our practice work for tomorrow's class, let's just review one final piece. Sometimes linear equations or lines are not written as linear functions. In these cases, we need to solve the equation for y. So again, we're used to seeing linear equations written as y equals mx plus b, where m is the slope and b is our y-intercept. Sometimes we just have to go through the trouble of reorganizing a given equation to look like this. And again, our goal is to get y by itself, or to solve the equation for y. So let's see what we can do to make that happen here. If it were me, I would start off by subtracting x from both sides of this equation, and that would leave me with 2y equals negative x plus 6. I wouldn't call it 6 minus x here because that's generally not the way we would write a a slope-intercept equation. We generally like to have the x in front of any constants. Now the last thing to do in order to get y by itself is to divide both sides by 2. And what you'll see is that we do isolate y here. And if we divide by 2 on both sides of the equation, that means we have to divide both pieces, or every term, by 2. Now this is the same as negative 1x, and when negative 1 is divided by 2, we receive a result of negative 1/2 x. And 6 divided by 2 is 3, so we have now the solution written in slope-intercept form. This equation that we started with is the exact same as the equation we finished with here. We've just rewritten it in a different form. There's a typo here. This should be 2x plus 3y plus 4. Let's work to get this one by itself. Solve for y. So the first thing that I would probably do is try to isolate, there we go. I would like to isolate 3y. So what I'll try to do is subtract 2x from both sides of the equation, and I'll also subtract 4 from both sides of the equation. What that'll leave me with is 3y equal to negative 2x minus 4. Then I will divide both sides by 3, and that'll leave me with y by itself. Negative 2 divided by 3, we can't really simplify that, so I'll call it a fraction, negative 2/3 x. And negative 4 divided by 3 can't be simplified either, so we'll call that a negative 4/3. And this would be perfectly fine for a final answer. Y is equal to negative 2/3 x minus 4/3. Thanks for following along with this long video today. I made it a little bit longer because of the snow day that we had yesterday. I wanted to make sure that you saw several of these examples as well as a preview of some equations that look like this at the bottom where the given equation is not written with y by itself. That should give you enough information to get started on the practice problems. I realize you don't have a copy of the practice problems. Those were going to be handed out today, so I'll try to make a copy of them available and post it online. Please give those a try before we come into school tomorrow. Otherwise, we'll be working on those together in class.